Hey folks, I'm here on behalf of EarthGames.com. EarthGames is a research opportunity for students at the University of Washington to code games that are both fun and educating, particularly with respect to climate science. For my project, I wanted to create a game involving the Earth, an Earth game, but I had a particular two-dimensional style in mind. So I wanted a 2D game, but with a 3D globe to interact with. In Unity, I played around with a couple different approaches on how to create this globe. Again, since this was a 2D game, I only used sprites, in this case pixels. However, the screenshots you see here are of the game scene in 3D mode. So the objects are displayed with perspective rather than isometrically. I also gave the sprites a Z position, as if I were making a 3D game, which doesn't do much in a 2D game, but helps me visualize my progress. In 2D mode, these spheres really just look like circles. So far in these screenshots, you see my first approach, which was to plot the Z position of the sphere with respect to X and Y, a rectangular coordinate approach. So I had two for loops that would vary X and Y, and set the Z position to be equal to the square root of the quantity X squared plus Y squared minus the radius of the sphere squared. The problem here was that the pixels became sparse as the for loops reached the extremes of the sphere, what one would call the asymptote. In these screenshots you can see this phenomenon occur at the equators of the globes. This wasn't a huge problem, except that I wanted the globe to be able to rotate on any axis. And the idea of recalculating the positions of all these pixels, while also heeding the sparsity of the equator, seemed like a mess. That's where spherical coordinates came in. This Unity library can construct and manipulate vectors in polar coordinate form, and convert polar coordinates into Cartesian coordinates and vice versa. Plotting the sphere with these was a lot simpler, and created an even layer of pixels. This is where keeping track of the z-coordinate of these pixels is key. Trying to plot a sphere with vectors in 2-space would be a nightmare. Here are the spherical coordinates in action, plotting each pixel of the sphere one by one. Again, I used two for loops, but this time I varied the polar angle and what's called the elevation angle. You can think of these two as latitude and longitude. What's nice about plotting a sphere in polar coordinates is that the other variable is simple. The radius, or the distance from the origin, is just a constant. So there were no equations involved. The next step was to rotate the sphere, which was also relatively simple, at least on the polar angle. The elevation angle is difficult, but more on that later. To rotate the sphere, I simply added a small amount to the polar angle of every pixel in the sphere. In this demonstration, I did this on every update tick, but you can imagine linking this behavior to a mouse interaction, such as swiping in a certain direction, which was one of my goals. Now I wanted to get closer to my original goal of making a globe of the Earth. At first I was thinking of manually painting a map with green for land and blue for water onto the surface of the sphere. But I ultimately settled on mapping the altitude of each pixel above or below sea level. This would have the side effect of demarcating where land is and where sea is, because anything with a positive altitude would be above sea level. This is where having organic skill in programming comes in handy. I found this website that queries Google Maps for the estimated altitude of a particular latitude and longitude. Now, there's probably a better way of doing this by directly interfacing with Google. However, I didn't need a long-term solution, so I wrote a script to run on the page to query for all the altitude data I needed. I had to wait half a second between each query just to make sure the server caught up, so all in all, the script took about 2 hours to come back with the data. Once I had my data, I added another sphere directly on top of the previous sphere. But this time, the radius of the polar vectors was a function of the data. The previous sphere I colored blue to represent the seas, which have an even altitude. And of course the new sphere I colored in different earth shades to represent the land, which is the uneven altitude that I gathered the data for. Note the aesthetic disadvantages this strategy had for me. The land and water tiles would sort of rise up over each other as the globe turned. Where the land had dramatic shifts in altitude, the water would peak out, as shown here in India. To somewhat solve these problems, I lowered the effect altitude had on each land tile's distance from the origin. But one disadvantage of this is that I preferred the aesthetic of the previous version. The greater variability in altitude gave the globe a more tactile look. Plus, the problems persisted. The easiest fix was to vary the z positions rather than the radius of the polar vectors. I shifted all the pixels whose altitude was positive forward by a constant amount, and those with negative altitudes backward by a constant amount. This guaranteed that every land tile corresponding with a water tile was either completely behind or completely in front of the water tile. As you can see, India looks fine now. An advantage of the previous method over this one is that it's easy to vary the sea level, which could be an interesting feature to play around with in the future. This is normal sea level, and this is low sea level. Notice how Alaska and Siberia are connected. The Middle East is connected with Africa, and the Mediterranean is an inland sea. This is high sea level. Australia is a small island. Siberia is almost non-existent. Europe looks like an archipelago. And only the Rocky Mountains and the Andes make up the Americas. There were advantages and disadvantages to all these methods, so I combined them. I still varied the radius of the polar vectors to simulate altitude, but I also pushed the land tiles with positive altitudes forward and negative altitudes backwards. which got rid of the pixels shifting around as the globe turned. This of course still had disadvantages. India still had a bit of water in it, and it would still be tricky to vary sea level. However, these were bearable problems for the time being, so I moved on to functionality, which I will discuss in the next video. Thank you for watching.